All right, our next presentation comes from Microsoft Azure, Mandar Gujrathi and Raymond Meng Tsai. How are you today, gentlemen?
Pretty good, thanks.
So Mandar, are you going to be co-presenting?
Yep. So
Fantastic.
Thanks, Brian. Hey, everyone. This is Mandar Gujrathi. I'm a technical specialist. And co-presenting with me is Raymond Tsai, who's a senior program manager. We both work in the Azure HPC and AI organization of Microsoft. So our topic today is supercomputing on demand with Azure. So these are the few things which I would like to talk in this presentation. We'll give you an overview of the Azure HPC stack. What are the different services and infrastructure which we have, the goodness of Azure for HPC, and how are we enabling some of our key customers towards the HPC workloads. We'll give you an overview of, from the compute side, what is available, how are we consistently updating our Azure HPC infrastructure, and some of the benchmarks which we have done. Gives you kind of a recommendation, which of those VMs are standing out, especially when you run these MPI jobs at a bigger scale. How can you put all this infrastructure, storage, how can you put together in form of a cluster and run your HPC workload? I'll be introducing you some of the HPC services which we have. And then I'll hand over to Raymond, who will give you a quick demonstration of the Azure HPC on-demand platform, which is popularly called as AZ Hub. How can you set up this HPC environment pretty quickly on Azure? So let's see what is the Azure HPC stack comprised of. So the key thing in the Azure HPC stack is the state-of-the-art VMs, which we've got, which is totally optimized for HPC. So Azure is the HPC infrastructure on Azure is purpose built, for the workload. And what I mean by that, we've got this CPU-enabled VMs, the GPU-enabled VMs powered by the fastest InfiniBand connection, which is available on any cloud, and that's present on Azure. Very often, as we have always seen, compute and storage go hand in hand, especially for this HPC workloads. So different kinds of storage services or mechanisms we have. We've got a lot of customers who love to have their data on premise, but spin up compute on Azure. So we've got this HPC cache delivering high throughput, high IOPS deliverables when it comes to HPC communications. One can spin up a BGFS on Azure. Azure is bringing up managed luster service. It's already in a preview mode. So if you're taking interest from our customers who want to give this Azure managed luster a try, so please come and talk to us. And also these NetApp files. Now, if you want an HPC-like performance storage, but not purely HPC, but on and off, you want to have this high throughput. So we've got this Azure NetApp files as well. And also Cray can be integrated with Azure. So you can have Cray computers, Cray systems in the Azure Data Center. You can leverage Azure services from the Cray cluster as well. As I said, InfiniBand, 200 gigs per second and consistently improving. Different kinds of workload orchestration mechanism. In this particular talk, we'll be pretty much talking about Azure Cycle Cloud, which is a great way of cluster monitoring, a workload orchestration tool, which will help you keep an eye on the budget, give access to the multiple users in your organization. And also lately, we have also enabled the Azure Kubernetes service for RDMA to leverage the InfiniBand through AKS. On top of that, if you want to go towards AI, there's lots of machine learning transformative services which enable you to do this end-to-end workload right from data ingestion to model deployment, integrating the CI/CD pipelines. So that's in general what the HPC resource stack is present now on Azure. While we bring these different kinds of or improved infrastructure for HPC, we also consistently try that out. And we have run specific benchmarks for different kind of applications, and we are adding lots of applications to the list as well. So we have a separate engineering team who have tested and stressed the system, how much you can, how further you can scale up. So there have been tests conducted on star CCM, ANSYS, weather simulations, molecular dynamics, and also A100 GPUs, especially if you want to leverage the A100s for deep learning workloads. So we have done all these things, and in most of these cases, we have received that scaling efficiency, and all those tunable parameters. We do have set some recommendations. So please reach out to us if you have any kind of a workload. If it's not delivering the performance, please reach out to us. We'll be able to help you out there. Next slide. So with this, we have recently embarked with a partnership with the UK Met Office. In the UK Met Office, we have been working consistently with them to optimize their unified model for weather simulations, and unified model has been shared with different kinds of weather agencies throughout the world. So if there is a unified model in place at your, and also with research organizations, if you're working with a unified model, please let us know and we can help you out, because we have got an equipment set up and we can easily do a pilot and see what the performance benefits we can achieve with your unified model. So with this partnership, it's running in 2 stages. The first stage is, the first 5 years is to deliver a 6 times performance over the current systems. This will be integrating the Cray supercomputers with the AMD Milan X processors. They will be leveraging, put in the Azure Data Center to leverage the Azure Services, and providing this 24/7, support, a managed supercomputing service. So that's what the first 5 years would be, and the second 5 years is to, help them use the native cloud-based supercomputing, build a huge data lake to accommodate 3.7 exabytes of data over time, and this is consistently enabling them and improving the productivity, whilst broadening the partnership in the weather and the climate field. The next slide. Yeah. Similar to UK Met Office, we've also partnering with Meta for their AI workloads. And this is the biggest cluster which we have set up for Meta. It's leveraging 5,000 plus GPUs, all using the A100 GPUs in place. And this is for the R&D organization to transform or to enhance the collaboration with PyTorch. Just going to run some deep learning algorithms in data parallel mode or model parallel mode. And this is all leveraging the GPUs and the Cycle Cloud service for cluster setup and cluster monitoring. This is another great addition which we've been doing with Meta for AI. So what is especially underneath this HPC infrastructure, especially on Azure? So of course, there are a number of VMs available in Azure, and on our cloud, it is pretty much classified by the letters. So right from A to N and beyond. So it could be an entry-level VM. So you could leverage these VMs to create a cluster. But if you really want to have that InfiniBand kick in, and these optimized, compute optimized or GPU optimized or memory optimized workloads with leveraging the InfiniBand, the HPC SKUs are falling in this bracket of H and N. So H are the CPU enabled machines and N are the GPU enabled machines, which comes with the InfiniBand in it. So let's have a brief peek at what the H series VMs deliver. So the latest addition to this particular bracket is the HBV3s, which have been powered by the Milan X processors. Each VM comes with 120 cores, and this is governed by this L3 cache, which gives a performance boost, especially for those big workloads where you want to run this big models of multi-million or billion cells for star CCM or ANSYS. So that's where the HPV3s, will deliver a lot of performance. HPV3s and HPV2 is one generation old, given by Rome. And both of these VMs come with the 200 gigs of HDR InfiniBand. Similar to HBs, we also have Intel-based SKUs, the HC series, and now they have been, currently they have the Intel Skylake. We also have Intel Ice Lake processors, and we're adding more to the list as well. Now let's see what different types of benchmarking we have done, especially with this compute, with the CPU VMs. So over here, there are two charts. On the left-hand side, you could see that how the different VMs perform, what's the performance of those VMs for an ANSYS model. The ANSYS model which we ran was comprising of 140 million cells. And you see a number on each bar. The higher the number, the better the performance. That's a solver rating. So you could see the Milan X is delivering, the solver rating for Milan X is over 3.5. So that is what is consistently outperforming in what we have. That's governed by the decent amount of L3 cache which it has. It's about 1.5 gigs per server, 96 meg per core. So that's what is helping Milan X to stand out in the HPC SKUs on Azure. On the right-hand side, we have seen as you throw in more number of VMs for the compute, you could see if you just throw 64 such VMs, each VM is having 120 cores, you could see you're getting about 200% scaling efficiency, and the workload is getting done at the fraction of the cost. Now, this is again, again, the L3 cache, the huge L3 cache, which is there, it's giving that performance boost, which is very, very essential for these highly scalable workload, because that enables us to improve the memory bandwidth and also the effective memory latency. So that's what is the main thing which we are gaining from the HPV3s. The next slide. Similar to this, we've also done some benchmarks on OpenFOAM, and OpenFOAM, again, Milan X has been consistently overperforming as compared to other VMs. So this gives you the best bang for the buck at the moment. And yeah, that is highly, especially for these highly complex applications where you have got multi-million cells to run in case of CFD workload, then Milan X kind of consistently outperforms. Similar to this, and weather simulation is also not far behind. So we've also done some benchmarks on weather simulations, and the same story holds true over there as well. More the number of VMs, we are gaining more speed up, 70% efficiency with 500 if you throw 640 plus VMs, especially for a WRF simulation. So the same story holds true. Now, while you're talking about the CPUs, let's have a brief glance at what the GPUs are going to be like. The GPUs on Azure are placed into three categories. The NC is a general purpose GPU for machine learning AI workloads. NV is for visualization, for rendering on Autodesk or CAD applications or seismic interpretation kind of workloads. And we also have this ND series specifically for the deep learning. So let's have a look on what that NC, ND, and NV stack looks like. So for the NC series, we've got a range of offerings, right, from K80s to A100 tensor cores. And at the moment, A100, we have done some benchmarks with A100 and compared with the Voltas and the Tesla T4s. So A100 is giving the best bang for the buck. It comes with a huge GPU memory as well. And it's pretty much, we have done some benchmarks for AI, also for genomics. So the net of that is the cost per job is very attractive when you go for A100 VMs. Similarly, for the visualization, again, we have got a range of flavors, right, from Tesla M60s to AMD MI25s. and also A10 tensor cores. So we're consistently upgrading as the infrastructure comes handy. And it's great to note that in terms of Melanix, the day when AMD announced their chipsets, we had on Azure immediately on the same day. So it was that's tied the partnership we have with all these vendors. Coming towards the ND series, specifically for deep learning, a range of them. We've got this ND A100s and ND M800s. ND is a standard memory. These have got 8 A100 cards with 40 GB standard memory. If you go for enhanced memory, that's where you've got M in there. So again, 8 A100s, 80 GBs of GPU memory. So these are governed by this NV-linked interconnect. They've got InfiniBand enabled, so it gives you best performance for this deep learning AI workloads. And this is exactly what Meta has been leveraging to see the boost in the performance. Now let's see what the benchmarks look like for AI leveraging these N series VMs. So if you have a look at the left-hand side over there, so over there are 2 bar charts. So the one in light blue is with the A100s, the one with the dark blue is with the V100s. So what we have done is we have benchmarked different deep learning algorithms, SSD, single shot detector, ResNet, natural language processing, and we've seen that, as I already mentioned before, that A100, the number of sequence processed per dollar is quite attractive. So it's giving the best bang for your buck. That goes in training. The same story holds true for inferencing as well. A100 is outperforming. On the right-hand side there, you see the number of, if we have compared the Tesla T4s, V100s and the A100s, the A100s are in gray. So over here, we are training a BERT algorithm with different batch sizes. Now, as you could see, for 64, 120, 256, it was the V100s and the T4s were not able to do it because they did not have enough memory in them. But A100s were able to train those algorithms. So this is what we have seen in terms of these training results. Now, as I said, we have tested A100s for genomic workloads as well, and dollar per, or the cost per job is pretty attractive on A100. So you can do a lot of things. A100 is also multi-instance GPU, so you can break that VM into 7 such GPU instances if you would like. Next, I'm going to just give you a brief overview of these Azure services. Now, if you want to have these VMs in place, connect with the storage, InfiniBand, there's a service called as Azure Cycle Cloud. Now, Azure Cycle Cloud, it is auto-scalable. So as you can customize it, you can bring your own choice of a scheduler. We do have got these templates, is customized for a scheduler, customizable for an application. You can add users, share the cluster with different users in your organization. You can put some budgets per cluster. You can check the access, how much a person is using. So all these job accounting kind of facilities are present inside this Azure Cycle Cloud environment. The next slide. So what it typically does is most of our on-prem users would love to stick to a specific scheduler. So that's the mechanism that we would like to give them the same look and feel what they are used to on-prem on Azure. So that's what Cycle Cloud enables you to do. You still work with a scheduler of your choice, the same storage of your choice, but on a cloud. To get started, most of the customers do have, they have investment on-prem. So they would love to stick to that investment for now. But as they run out of capacity, they would love to augment the capacity by using the cloud. So that's where Cycle Cloud can also be leveraged in hybrid mode. So if you would just use your cluster on-prem, but if you want, you can burst onto Azure if needed as well. So both the scenarios are catered, and it's highly customizable to your application, to your scheduling, to your storage. So that's the brief overview of Azure Cycle Cloud. Now I'll hand over to Raymond to take you through how to spin up these services and the infrastructure. Raymond.
Okay, thank you, Mandar. Hi, everyone. My name is Raymond. I'm a program manager and part of Azure Hpc AI engineering team and located in Taiwan. Today, I'm going to introduce you the Azure HPC on-demand platform. We call it AZ Hub. And I'm going to introduce you and demonstrate the end-to-end how AZ Hub can be working from the end user's point of view. So this is a typical HPC workflow from end user's point of view. A user might be, log into a login node using to be authenticated by a user directory services. And they might, upload the files to a shared file system and, work on some of the virtualization to see how the data works. And then submit the job through scheduler, whatever is a PBS, SLAM, or LSF. And then, provision the compute nodes necessary for these HPC jobs. And end user might also need to monitor the process of the jobs to see if it fails and check if it finished or not. So the main goal of AZ Hub platform is to will be to provide end user the similar experience as how they work, so they don't need to have a big learning curve when they are trying to run their HPC applications on Azure. So this is the vision of the Azure HPC OnDemand platform. It's trying to deliver a complete HPC cluster solution, not only for end user to submit their jobs, run their applications, but also for administrator to easily deploy and manage the cluster, and also for some other financial department to manage the budget, to manage the cost. So the target audience will be from the very small size of work group to an extremely size of organization. Like for example, if the enterprise, you are system integrators, you are just the individual software vendors, will find it very useful to deploy and just run whatever size of the HPC cluster you want. So those are the three main personas we focus on. We just briefly mentioned above, like for example, from the end user's point of view, they need to provide them the username password, and they would need to be able to SSH into the on-demand head node, something like that, and check the files and submit the jobs. And from an HPC admin's point of view, they would need to, easily to set up the cluster, manage the users and groups, set up the limitation and restrictions of their, privilege, and also, design and define the size of the storage solutions for this cluster, and also manage the, healthy situation, right, of the cluster. And from business point of view, you might want to do the cost control, and you want to set up some budget limitation, so that and also see some report or dashboard. So there are AZ Hub can provide all the functionalities or features needed for these three personas. So this picture is a high level of how we build up this platform. You can see that the platform is built on the Open On-Demand project, which is open source project from Ohio Supercomputing, and it's been managed and also be used for many universities or organizations worldwide. So actually, we are built on top of this project to provide a universal web portal. Also, we have integrated some popular schedulers, including OpenPBS and SLAM. And raster file system is introduced and integrated, and the Azure NetApp files is integrated, and Azure Cycle Cloud is integrated as well. So this is at a high level how we build up the platform. So now I'm going to switch on to my desktop to show you some end-to-end demonstration of how we build up the AZ Hub and how it works. So this is the it's open source and it's still ongoing. So many contributors contribute and give the feedbacks and report contribute to the repo, so everyone can contribute on this one. So let's see. Okay, so this is built on the on-demand portal, and Azure Cycle is here, and OpenPBS SLM is currently integrated in this platform. So it will be easy if I just clone the location. Let me see if I can. You will get the latest release of this AZ Hub. So if I try to look at the config file, you can see that there is we are following the infrastructure as a code concept. Then there will be only one config file you need to manage, and this is a YAML file, so that the Terraform we can utilize Terraform to build up the end-to-end cluster build up, so you can easily to integrate of yours into your existing DevOps pipeline, or even check out the version using your version control to see what's the different cluster you want to create, you want to build. So over here you can see that you can set up where's the location you want to build up the cluster, what's the name of the cluster, and some other important thing is that you can define your network topology over here, subnet definition, and the important thing is that you might want to manage your users and groups right over here, and then if you want to add update or delete some of the users or groups, you can just do it over here. And here is that you can specify what's the OS version you want to provision when you have your computer nodes available. So like for example, CentOS 7.9. And then over here, then you can specify, which skill, like Mandar just mentioned, we have the H series, N series for GPU skills. Then what's the limitation the cluster can provision, right? So after that, you can create your cluster. So let me show you the one the cluster we just created to have a overview of how it's been working. So you can see that it's powered by Open OnDemand project. So this web portal will be a similar portal over here, and we integrate many capability over here. So the first thing is that for the virtualization, users might to use the virtualization node to do the to do the rendering thing or something like that. So you can specify with a GPU or without GPU. And for example, over here, I'm going to provision. I need 1 hour of the Linux desktop, so I can just launch it. And before it can be launched, I can see, there's a file, so you can browse the file systems, and you can upload and download files over here. And if I switch to the previous directory, you can see there are many users has been established, right? So I'm actually logged in as a Meng TSAI. So if I try to log on to it to see what other users folders, of course, its permission is denied. And let's see if I can really run some jobs over here. So actually, I open a terminal and which connecting to the on-demand node. So over here, I can see, here is my location. I'm logging as the Meng TSAI. So this is my location. I can do the list, and I can check what's the storage is being specified. I can upload or download files over here. So you can see there's the Azure NetApp files, which have 8 terabytes, and we have the raster. We have 2 and 4 terabytes. So which all these information, size, definition can be defined on the config file I just showed you. Okay, so let me try to just do some. I'm using PBS, so I can do some QSub to submit the jobs, and I try to provision 4 nodes to execute the some dummy jobs over here, just doing some sleep, right? And the slab type is execute. Okay, so this is the 3640. This is the job ID, so I can like check the how it's working on the work queue, which is the default queue, and I can also, of course, check the queue, the status of every queue over here, and if it's been of course, I can check the PBS nodes over here, right? So this is how you can work on this terminal. Then I will switch back to the dashboard. Then I can check the cycle cloud. Mandar just introduced that is well integrated into the cycle cloud. So actually, from the cycle cloud, you can see some UI and manage the cluster, manage the nodes over here. So remember that I just submitted dummy jobs with 4 nodes, right? So you can see here there's I try to do some execute, and there's 4 nodes because every node has two CPUs. So total core is 8 cores over here. And as Mandar just mentioned that on Azure side, you have different kinds of skills. Like for example, H series is some HPC specific skill with CPU available, and N series is for GPU available here. So you can actually, I just did is to do the execute as the slot type, right? So it's only 2 CPUs per node. So this is the cycle cloud cluster. You can manage and see what's going on which users submit the jobs, and you can check the status. So it's easy to manage, and also check the see if there's any. You can set up the new alert, because like for example, if some users already achieved or near the budget. So this is cycle cloud over here, and then let me switch back to the dashboard. So this is from end user's point of view. So like for example, you can check the active jobs. Then you will see, okay, there's some of the jobs already I just submitted, right? One is from the standard in, I just submitted over here. And from the IT admin's point of view, you can check the Grafana is integrated by default, integrated in the system as well. Let's see. So I will check the dashboard, so I can see all the nodes, all the computing nodes, head nodes, schedulers, information in this cluster. So at once. So I did some work over here, so that you can see there is some processes over here, some RAM usage, CPU usage, and you can of course enlarge over here. So this is basically a quick demonstration of how this HPC look like from the end user's point of view. So let's back to my slide. I will just skip all these screenshots because all those I have a real demo over here. And the thing I didn't do is that once I provision a Linux a desktop with a GPU available, you can do some GPU acceleration to run your jobs with the acceleration without acceleration. Then you can see the difference. This is the one without GPU, only utilizes CPU. So it's the rendering speed is relatively slow. If you utilize GPU, it will be higher. So this is just a quick wrap up. how we built this Azure HPC platform. You can see that we utilize Terraform. So it's infrastructure as a code concept, and you can easily to manage and configure the whole infrastructure as one config file. And also we integrated Azure NetApp files and blob and logsters, and we use Azure Directory for identity. And you can and Cycle Cloud do the auto scaling, scale up, scale down, and OpenPBS Slurm. It's been integrated over here. So this is the appendix of the all our presentation, including the GitHub, where you can get the latest release of the Azure HPC, as well as some of the latest benchmark information of the deep learning examples. Okay, so here is our presentation, and hopefully you have a great afternoon. Thank you.
Thank you, Raymond. Appreciate the demonstration there. I do have one question that came in. What is the largest HPC VM I can deploy in Australia?
HBV2s, the with 120 cores. So that's on the CPU side. HBV2s are available in Australia. If you want to go for the GPU, we've got the NCV4s with it, which has the A100s.
Okay. The next question was which data centers have the GPUs? I think you hit on that. Sydney.
Sydney.
Okay. Okay. I currently don't have any other questions in the queue. So Mandar and Raymond, thank you very much for presenting. I really appreciate it.
Thank you.
Thank you.